Good morning. My name is Beatrice Zambotti. I am a PhD student at CNRS, and I recently graduated with a master's degree in mechatronics engineering at the University of Trento. My master thesis, which is the culmination of an internship at CNRS, is titled Modeling and Control of an Impacting Electromagnetic Actuator via Hybrid Lyapunov Techniques. Electromagnetic actuators are devices that leverage the principle of electromagnetism to convert electrical energy into mechanical energy. They consist of an electromagnet, which is used to control the position of the moving part, and they are designed to operate within a limited range of positions, which causes impact between the structure and the moving part. To account for the mechanical impact, we introduced a hybrid dynamical model, which combines a continuous time and a discrete time dynamic and allows us to describe the update in the velocity, which is reversed in scale every time that an impact occurs. Moreover, diverging from most approaches, we derived a magnetic force and inductance model that includes the effect of magnetic saturation and flux fringing. Based on experimental data and theoretical derivation, we proposed two different models, one which is used for the model validation and the other one for the control design. The goal of the control part of this thesis is to find a control law that asymptotically stabilizes the origin of the hybrid error dynamics. A first solution is to ensure a quadratic Lyapunov decrease along the linear rise, flow, and jump dynamics. So we design an LQ-based controller where the gain K is selected by solving the following optimization problem, and we prove asymptotic stability of the origin of the hybrid system. To increase the closed-loop performance, we propose a nonlinear control strategy based on the backstepping, which induces a larger basin of attraction. We initially stabilize the mechanical subsystem with a virtual control law, and after that, we derived a stabilizing control input calculated based on the energy Lyapunov function, which consists of the sum of internal energy of the system. As we can see from the simulation, the LQ controller stabilizes an equilibrium point, but if the system is initialized too far from the set point, the state diverges. On the other hand, the backstepping control law is more robust and stabilizes the state even if it's initialized far from the desired equilibrium point. This work was already presented last September with an oral presentation at CIDRA and is currently being translated into a journal paper upon completion of the experimental testing on the prototype. Thank you for the attention.